Hi again, Professor Bob Young here, and in this instructional video, we're going to look at what's called translations, stretching and shrinking of graphs, and reflecting graphs. Now, don't let this next graphic scare you here, but we're going to look at a whole bunch of different functions. Now, can you all tell me why every single graph on this page is a function? Well, looks like all of them passed the vertical line test to me. And also, each x value would differ. So notice we've got the constant function here, f of x equals 2 or y equals 2. The identity function, y equals x, where x and y are always the same number. So to graph the second graph along that top, you would say when x is 0, y is 0. When x is 1, y is 1. 2, 2, negative 1, and so forth. Our friend the linear function, the graph of a line, and hopefully y'all remember this is in slope-intercept form. Notice I started at -1, went down 1, right 2. The square root function, y equals the square root of x. Now some review things we can do here on the square root function is remember that x must be what kind of number? Either 0 or positive. So if you wanted to, on the square root function, now what I don't like is I should have put arrows on all of these. Graphs should always have arrows. Why didn't I do it? I think in your supplemental handouts I gave you in class, if you're a lecture or hybrid student, or you can get in Angel, have all the lines on them. So I didn't shortchange anyone, but we could talk about the domain of this graph. Starting, the x values go from 0 to infinity. So a little bit of review here. And the range, the y values, also, notice both places start here, which is also from 0 to infinity. Notice we're putting the bracket to include 0. So on x, it goes that direction forever. On y, it goes up slower, but it eventually heads toward infinity. The squaring function, gee, I wonder why they call it that. Y equals x squared, a quadratic equation. I want you to start thinking parabolas when you get over here. All right, so when you have y equals x squared, the squaring function graphs a parabola. Y equals x cubed, I like to call this the S. Don't mess with the S. It's a wavy, snaky creature. All right, and to get these graphs, of course, we could always get ordered pairs here, and we could plot ordered pairs for y equals x cubed. We can say when x is 0, y is 0. When x is 1, 1 cubed is 1. When x is 2, 2 cubed, 2 times 2 times 2 is 8, and we could come over here and we could plot these points, and you would see them form the S, and you could put negative values in for x and so forth as well. Rational functions, y equals 1 over x. Notice x can never be 0 here, or this one's going to be undefined. So when you start putting in values for x here, this is what it looks like. You're going to get, I call this one the hooks. Absolute value function. We're going to play with this one a lot today. I'm going to go colors on this absolute value function. Now notice the absolute value function, the two words absolute value always start with what? The two words start with this, A, V. And when you graph absolute values, that's what you get is a picture of A, V. So just remember that. Now, exponential and logarithmic functions we're going to talk about more in Chapter 4, so I'm just planting seeds in your mind now. We'll come back to those, but they are functions. Now, next thing we're going to do is this next graphic might even scare you. There's a whole bunch of things. If something's a function, you know those old Wild West shows where you'd have a guy come in the old Western tavern there, and he'd have his gun drawn, and you'd always have the fast shooter, he goes, draw, partner. And then we're going to make these graphs, these functions, dance, just like some of those sharpshooters. They'd shoot at people's feet, and you'd see them dancing and stuff. They were so fast. We're going to make these graphs dance. All right, so looking at these 8 steps here, and I'm just going to quickly go through them, and then we're going to go through them as we get through the video. If you take any function and add or subtract a number on its rear, and they call this number k, it's either going to move the function up that many or down that many. So these are called vertical shifts. Notice if the number is inside the f of x. So they pick another number called h here and put it inside there. It's either going to move it left or right. These are called horizontal shifts. Now these are dangerous ones because these shifts the directions you don't expect. So we'll show you a whole bunch of these in a minute. If you put some number in front of a function a here, if that number is greater than 1, all right, it's going to do what's called a vertical stretching. If it's between 0 and 1, if it's some fraction, it's going to do what's called a vertical shrinking. Now, Young says on this, vertical stretching, I'll talk about it later. It's one of the strange things here. All right, and if you take that, and this also talks about that as well. Now, notice on 7 and 8, if you take a function and you negate it, it's going to reflect it about x, but if you put the negative, if you negate the inside, it's going to reflect about y. So, and I'll come back to this as well, but let's just show you some examples here, and I think y'all will get it. All right, so I'm going to stay with pretty blue like they have here. So this graph in the middle is some function f of x. So this is demonstrating the vertical translation. So if I go adding 2 to f of x, notice every point gets shift up 2. So 0, 0 goes to 0, 2, and every point along that curve gets shifted as 2 as well. If it's got a -3 on it, it just takes that middle one and shifts everything down 3. And this works for all of our functions. Every single one of these that we talked about, ladies and gentlemen, if you go adding and subtracting numbers on their rear, it would shift them up or down. Pretty cool, huh? Make them dance, partner. So here's our friend, the absolute value, or the v. So we put the regular one we've talked about here. Now, of course, if we want to get real fancy in graph, we want to get some ordered pairs. So what we're going to do is we're going to say, how do you get that original v? So we put some table of values in here. So we say when x is -4, y is 4. And if you want to, we can plot these points in blue here. When x is -1, y is 1. When x is 0, y is 0. And then we've got 1, 1. And you can start seeing the v here, 4, 4. So don't be afraid of graphing. You're just substituting in values of x to get values of y, and hopefully you'll start becoming more familiar with these shapes. Now notice what happens when you put that -4 on the rear, and you plug in those same values, everything what? Goes down 4. Now, horizontal translations, it says if a function g is defined by g of x equals x minus c, where c is a real number. Now, this is where the book starts. Everyone looks here and goes, man, I don't get that. And they start reading this. You can't read and learn in math. I don't know. Maybe some people can if you really have good notational values. Then for every point x, y on the graph of f, there will be a corresponding point x plus c on the graph of g. The graph of g will be the same as the graph of f, but translated c units to the right if c is positive, or the absolute value c units to the left if c is negative. The graph is called the horizontal translation of the graph of f. Now, did y'all get that? I didn't think so. Now, notice what Young puts here. Horizontal translations shift the direction you don't expect. So if the original graph is f of x, if you go saying f of x minus 3, you might expect it to go left 3, but in reality it goes what? Right 3. So be careful on these horizontal translations. If it's f of x plus 2, you might expect it to shift right 2, but it shifts left 2. Every single point. So be careful. All right, so here we're taking our friend the v, and we went through and we plotted those same points in red there. All right, now notice what happens if we take those same values. And now why does this shift right 4? If we put 4 in for x, the absolute value of 4 minus 4, and see, that's how they're getting this, by the way. They're just putting in x values there. Comes out the absolute value of 0, which is 0. So when x is 4, y is 0. So this is really good to see how this thing, everything shifts 4 units the direction you don't expect. So if it's inside there, it shifts that way. All right. Now, how'd they get this point, Young? Here. Well, they took the absolute value of 2 minus 4, which is the absolute value of negative 2. Now, you have to remember, absolute value always comes out what number? Positive. So notice 2, 2 on the blue is here. So every point on the red shifted 4 units right, horizontally. Now, notice this caution here is pretty good. Like that other one I read, y'all might have been scratching your head, but it says, determine the magnitude and direction of horizontal translations. Find the value that would cause the expression in the parentheses to equal 0. So, for example, the graph of x minus 5 squared would be translated 5 units to the right of y equals x squared. See, because if you put a positive 5 in here for x, you get 0. All right. On the other hand, the graph of y equals x plus 5 quantity squared would be 5 left. And this is, again, if you plug in points, you'll see that, because if you put negative 5 in there, you'll get 0. So that's another good way to check. All right, now we're just going to take some more and graph them. So we've got this function on the bottom here, and I wish they would have kind of used different colors to show things. You know how I like to do colors. All right, so if we take this function, and we want to say, what is f of x plus 3? We're just going to take every point on this one, and we're going to raise it 3 units up on this nice piece of graph paper. So no, every single point is just getting, no matter where it is on the function, shifted 3 units up. I'll get this one. They didn't really get that one. And then they just draw the curve. So notice that if you have a vertical translation, the picture really doesn't change. It just moves up or down. Or if we take that function f of x, now why didn't they use different colors here again? Fortunately, don't worry, Young's got your back. All right. Now this one, since the plus 3's on the inside, it's not going to be vertical but horizontal. And careful, this one shifts the direction you don't expect. So in other words, if I go taking this point here, notice it shifts if I plug it in 3 that way. This point on f of x shifts 3 that way. This point, every point, and you still, even when you shift horizontally, just like vertically, notice the graph does not change shape. Oh, now they're getting really funky, Young. So they're taking this f of x here. And you know what I tell students to do in class is if you got a function here, if it's got a plus 3 on it, that tells me it's going to vertically shift up 3. If it's got the minus 2 inside, which way? Oh, they're trying to trick you here. Be careful. Right 2. So every point on the function f of x is going to shift 2 to the right horizontally and 3 up vertically. So, and if you wanted to take the rest of those points and do it, you could, and get, again, notice the vertical and horizontal shifting does not change the shape of the graph. Next, reflecting. We're making these graphs dance just like in the old westerns, making people dance. Forming a mirror image of a graph across the line or axis is called reflecting the graph across the line or axis. It may even get back to our symmetry test we've talked about. So notice if we're given a function y equals f of x, if we put the negative, if we negate a function, it's going to reflect it about the x-axis. And we're going to show this in some pictures. If we take the function y and put the minus on the inside instead of on the outside of the function, negating whatever the function is inside, reflects it about y. And again, we've talked about this. All of the pictures, all of the rules are in this graphic. So we're making good progress. All right, so notice if we take our friend the square root. All right, now we know that the square root looks like this far right end one here, the normal square root graph. Y'all seeing that? Now, watch what happens on our friend the square root if we put a minus on the outside. So notice again, they plotted some points, they put some x values in here, and they got some y values out. All right? So if you were to plot in red here our normal square root friend, it comes out, it reflects about the x-axis. So putting the negative in front of any function will reflect it about x. And I mean any of them. But if we put the x on the inside and we did the same thing, now notice here we have to be careful, because if we put a -4 in here, the negative is underneath here, we get undefined creatures. But if we put a -4 in here, we get the square root of minus a -4, which comes out the square root of 4, which we can get values from. Now notice that what happens here when that minus is on the inside, like I promised, it doesn't reflect the graph, the normal graph about the x-axis, but the y-axis. All right, now it says graph this function here. Now don't read the solution or anything. I want y'all to look at the problem here, the equation. Now this is going to be a v again. I'm hoping that you're starting to learn what some of these would look like. So we're going to take our normal friend y equals the square root of x, just to see if y'all are getting this, which would start at 0, 0 and look like this. Now when I'm looking at this graph and I'm telling students to look at it, what's this +1 here on the end mean? Well, it's going to shift 1 unit up. How about the +3 on the inside? It shifts 3 units left, the direction you didn't expect, but this one's even better. Oh, they're just getting better as time goes on. We've got a minus out front here, which reflects it about which axis, x or y. Well, this is going to be an x-axis reflection. So let's see what happens here. Now, see, if I'm going to graph this by hand, this translating and reflecting and stuff really helps me, because I know that if my normal absolute value started at the origin, that I need to go up 1 and left 3 to start here. So I would go over -3 on the x, which would give me, if I plug -3 in for x, +1. See, so that would really help me. And then this x value, or this negative value in front here, tells me it's going to flip it about the x-axis. And you'll see this when you plug in more points. Now, again, if you weren't sure how I got this first point, I'm just taking in and plugging in -3 wherever I see an x. So this is like evaluating functions earlier on. And we would get the absolute value of 0 plus 1, c would be 1. And then if I put -2 in for x, we could evaluate the function at -2. And what are we going to get here? Well, let's just do that one real quick. Minus -2 plus 3 inside the absolute value plus 1 gives us minus the absolute value of 1 plus 1. Now notice that minus is outside the absolute value, so that makes this a -1 plus 1, or 0. So at -2 we get 0, and then we could still plot enough points to see the v. Now students will say, Young, how do you know if you've got enough points to see the v? Well, you keep plugging in here. Let's do one more. -1, you're going to get the absolute value of -1 plus 3 plus 1 would give us the absolute value minus the absolute value of 2 plus 1. So we would get a -1. So at -1, we're at -1 here. And then I would say, well, do you see the v? And students will go, no. So then you would have to try some points like -4 and -5. See, but this shifting here tells me where I could look to get other values. So I know the tip of the iceberg is going to be right there. So very useful. All right, last thing, and we're almost done here. So this is kind of a long video, but it's got lots of good stuff on it. If you put, now none of the things we've done so far has changed the basic shape of the graph. All right, we have moved them left, right, up, down, flipped them about x, flipped them about y. But if you go putting numbers in front, you're going to see things happening. Now, if you have some function and you have an a number in front of it here, they call this a vertical stretching when that a number is greater than 1. Now, Young says this, and I'm not even sure this is a word. I call the vertical stretching the graph getting skinnier. I say get skinnier. If this number's like a fraction or a decimal in front of here, so notice if a is between 0 and 1, they call it a vertical stretching. Young says gets fatter. I know what y'all are saying. What is he doing here? All right. Also, if you put in values inside the parentheses here, then things are going to happen as well, but we'll get to those as well too, and we'll show you some stuff. We can bring those values inside out and still play the games here. All right, now it says graph the function. Here's our v with a 2 out in front. The a number is 2. Y'all think it's going to get fatter or skinnier. We will plot points and show you that this v, the normal ones in red, look, it's on like the weight reduction plan. It gets skinnier as you put a number in front. So this is the time, shrinking or stretching, when you put numbers in front of there, that the actual graphs change shape. Now what if we put 1/2 in front? And notice again, they put values of x in, they get the absolute value, they do the 1/2 absolute value of x, and with that 1/2 in here, the red becomes, this graph here is getting fatter. It's like it went to McDonald's and had nothing but Big Macs and quarter pounders. So if that number is a fraction or decimal, it goes woo. That's bad, isn't it? Now here's what I mean by putting numbers inside, like with the absolute value. Notice we got the old absolute value property here that I don't know a lot of you have seen for a while, but you probably did back in high school or something. And it says the absolute value of a times b will equal the absolute value of a times the absolute value of b. So if we were to take this absolute value of 2x using that property, we would get the graph we had in part A, looking back on this video. See, it would be that the skinnier of the v's. Or let's say we have a graph and we're doing this one. Notice this one you could factor a 2 out of, use the absolute value property. And what I would look at here is we're going to have a v shifted which way down here? Would it be shifted right 2, left 2, up 2, down 2? Well, this one would be shifted a horizontal shift of 2 to the right. And what does this 2 out front make it skinnier or fatter? We will see. I think it's going to be skinnier. Yes. So notice they just got some points here and plotted. So this will help you as well as seeing this graph. Now then they give us another one. Well, what if they put a minus sign out here? What's going to happen if you negate the function? Well, it's either going to flip it about x or y. Do you remember? So this technique will help you, and it would shift it about the x-axis. All right, so if we just put a minus out there, this graph here would look like, and I'll just kind of, I better get my line tool out for this one. And I hope y'all think this is good here. I thought that was pretty good myself. All right, so that negative out in front would definitely impact things because it would change this into this. Dun, dun, dun. And finally, what if you took minus 1/2 x squared plus 4? Now, this is going to be the graph of it's a squaring function, a parabola, all right? So this parabola, let's look at some stuff here. With that plus 4 on its rear, and I'll go to a different color here, would be shifted vertically up 4. All right? The 1/2, would it make it fatter or skinnier? Well, it would make it fatter So here's what we're doing this lesson. The negative would flip it about x. So it would flip about x. So let's see if we can see that one here. And this video is getting a little bit longer than I wanted. So if you actually started putting values in there, look at that. Ooh, a heavier parabola. Shifted 4 up. All right. So finally, in review here, any of these functions we can make dance by either adding or subtracting a value here we call k to shift it vertically up or vertically down. If it's inside, it will shift it. Maybe this will make a little more sense now. Left or right, watch out, those are the ones, the direction you don't expect. All right. The A number, either these are the ones that make it change shape here. All right, fatter or skinnier. And in review, a minus on the outside of a function flips it about x, while on the inside flips it about y. Professor Bob Young signing off.